In the previous video, I showed you how to find a rate law when given concentration and time data. In that video, we used an integrated rate law for a second order reaction. This video is meant to show you the same information with a first order reaction. You'll notice I already have my column for natural log of concentration versus time. Enter some values, negative 0.1054 for the first data point, negative 0.2323 for the second data point. Then I'll skip down to the bottom. The second to last data point is negative 1.1215, and then the last data point is negative 2.1371. And remember, I can ignore the middle data points because I really just care about the slope at the top of the graph and the slope at the bottom of the graph. This one's a little tricky because the time intervals change. The first time interval is 10 seconds. The last time interval is 80 seconds. So I can't at a glance sort of tell if these are actually linear or not. When I calculate the slope at the top, I get negative 0.0127. And the slope at the bottom is also negative 0.0127. Remember that this tells us this is a first order reaction. So rate is equal to K, and in this case, K is the negative slope, so 0.0127, the slope of this is 1 over seconds, times the concentration of A to the first power. Our integrated rate law will be the natural log of concentration of A at any time t is equal to the negative rate constant, in this case 0.0127, times t plus the natural log of the initial concentration, which in this case is 0.9. To find the half-life for this equation, or for this reaction rather, the half-life for a first order equation is simply the natural log of 2, or 0.693, over k, which again 0.0127. And when I do that, I find that the half-life for this equation would be 54.6 seconds. When I go back up and look at my time data, 54 seconds is shortly after 40 seconds, and so we've gone from 0.9 down to 0.5. It stands to reason that the half-life time will be between 40 and 80 seconds, and 54 is just fine with me. For the next problem, you do not have this problem in the packet that I gave you, but I'm going to pretend that the next question said to find the concentration of A after 100 seconds. And so I'll say the natural log of the concentration of A after 100 seconds is equal to negative 0.0127 times 100 plus the natural log of 0.9. When I solve this, I get that the natural log of the concentration of A at 100 seconds is equal to negative 1.375. And when I solve that, remember you can sort of undo this by doing e to the natural log of A at 100, which is e to the negative 1.375. And so we find that the concentration of A after 100 seconds have passed is 0.253 molar. Again, I always like to check. So 100 seconds would be shortly after 80 seconds, and at 80 seconds it's 0.33 molar, and so it makes sense to me that about 20 seconds later the concentration will be slightly less, 0.253. I'm going to pretend that the last problem was that I needed to find the time at which the concentration had fallen to, let's say, 0.2 molar. And the way I'll do that is to say the natural log of 0.2 is equal to negative 0.0127 times time plus the natural log of my initial concentration, which is 0.9, And when I solve, I find that the time for that to happen is 118 seconds, which we don't have to scroll up far to see that that's reasonable, because the concentration was 0.2 at 100 seconds, so it makes sense. Oh, sorry, not 0.2. That was awful. The concentration was 0.253 at 100 seconds, so it makes sense that a little bit later, 118 seconds, the concentration would have fallen even farther to about 0.2.